Hello, this is Dr. Kraus with a video on homogeneous transformation or HT matrices as part of my engineering robotics class, EGR 445-545. This is kind of a second part in that class lecture series. I am planning to just kind of make this generally available in case it's useful to other people who aren't in the class. So I add just a few more details than I would for my students. So kind of the big idea is that we want to model any robot using a series of HT matrices. These will come from the Denevit-Hartenberg convention as part of equation 3.6 in the book that we're using, John J. Craig's Introduction to Robotics book. And so each of these models one robot joint and link combination. We'll talk about that when we get to chapter 3. But the idea here is that each of these is both a rotation and a translation, potentially actually 2 rotations and 2 translations when we get to here, one along X and one along Z. But we want to multiply these together, so each of these needs to handle both translation and rotation for us. So what we need is a way to take a vector that's known in frame B and map it back to frame A. But frames A and B were initially aligned. We translated parallel to frame A, and then we rotated. So what I mean by that is we start with frame B on top of frame A. We translate first, and we translate parallel to XAY. So we're in the frame A components. And then once we get to our final position, then we rotate. Now this can be done 3-dimensionally. I'm doing it 2-dimensionally only because my drawing skills are somewhat limited. Yeah, that's not super pretty. So the idea here is that we would have some XB hat, YB hat, with some angle of rotation from or about the Z axis, the ZA-ZB axis. But before we did that, we actually displaced what we're calling PB org A. It's a vector from the origin of frame A to the origin of frame B, but it's in the frame A components. And then we have some point out here, P, and so this vector would be P in frame B. But what we're ultimately trying to find, and somehow I always manage to label my vectors in an unhelpful way that later comes back to bite me. So this is P B org A. This is PA. And so we know, hopefully from like physics or something, that if I take 2 vectors and add them head to tail, that would work. So we'd want to be able to write that PA is equal to PB org A plus PB. The problem, though, and we'll get into this in the slides in just a minute, is that I'm not allowed to add vectors together if they're in different frames. So I also need to rotate frame B into frame A components first, and then I can add them together. So I would take this vector and I would find its components parallel to frame A, and then if I wanted to find PA, I could add the blue ones together to get the Y components and add the red ones together to get the X components of PA. So this plus this gives me PAX, and this plus this gives me PAY. Well, these components are this. I'm taking PB, rotating it into frame A components, and then I'm adding it to this. So the key idea here is that the addition is taking place in frame A. So again, take this P. So we start with the frames on top of each other, and the order of this is really, really important. So I want to go over this one more time. We start with frame B on top of frame A. We translate it in frame A components first, and then we rotate. When we're mapping, we then go the opposite direction. We take PB, rotate it back into frame A components, add it to PB org A to get PA. So the claim is that if we need to somehow combine this multiplication or rotation represented by multiplication and translation represented by addition. We want to combine those together in one operation so that we can just go boom, 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 boom for each link of a robot. We'll have one frame attached to each link, and we will take P tip 6 and get it back into frame 5. Then we'll take that P tip 5, get it back into frame 4 as we multiply. So the claim is that if we put a 3x3 rotation matrix in the upper left corner of this thing, have a 3x1 PB org A, and then append a 0, 0, 0, 1, we'll have a 4x4 matrix that represents this equation. That's what we're trying to accomplish. As I already mentioned, so if I had a P that happened to be along the x-axis, I can't simply take 1, 2, 3, 4 in the x, 2 in the y, and add another 3 in the x and get the correct answer for a vector from this origin to there. So I have to remember this order of operations. I translate, and then I rotate, and so when I map, I've got to go backwards. And so first I take P, I find its components in XA, YA, and then I add them together. Sorry that my reds and blues don't match up with my hand drawing, but you get the idea of what I'm trying to do here. So we got to get into the same frame and add. So again, if we took that, so this is a 3x3, this is a 3x1, so altogether this is a 4x4 multiplying by a 4x1. So PB will multiply this 3x3, 1 will multiply this 3x1, and then 0, 0, 0, 1 would zero out this, and we would get 1 times 1. So, as an example, what if I had an RZ rotation, which is the problem that we were just talking about, an arbitrary XYZ translation, so this is my PB org A, and if I was multiplying that by some PBX, PBY, PBZ component, one of the questions that had come up from my students was, how do I just slap this 1 at the end? What does all of this mean? And so what I want you to see is that if we took this row and dotted it with this column, we would get the first row of PBA, or the X component of PBA. So we would get cosine theta times PBX, negative sine theta times PBY, 0 times PBZ, and X times 1. And so this is that dot product of the first row of TAB with our PB vector with the 1 appended. Similarly, second row, or the Y component of PA, sine theta times PBX, cosine theta times PBY, 0 times PBZ, 1 times Y, and so this is happening. And then this third row, 0 times that, 1 times PBZ, and then Z times 1. And then the bottom row, like I said, 0 times this, 0 times that, 0 times that, 1 times 1. So this 1 that's appended to the bottom of our position vector is allowing us to take this column and add it to our PB rotated into frame A. So this is the normal stuff we would have multiplying RAB times PB, and then we're adding in X, Y, and Z to get that additional translation, and then we have the 0, 0, 0, 1, so that it's really important that when we do this, we end up with our position vector, but also have a 1 at the end, so that if we needed to translate it to another, transform it to another frame, we could multiply. We're ready to multiply by another 4x4. So this needs to be a 4x1 result so that it can multiply by the next matrix. So one of the students was kind of asking, why does this need to be here? Let's just get rid of this row. So if we did that, we would have a 3x4 times a 4x1, which is technically legal in terms of matrix multiplication. But the result would be that we only get, it's the same as these three rows, but we would not get this 1 at the bottom. So if we neglect this row altogether, we get the correct answer for the x, y, and z components of PA, but we do not get the 1 at the bottom. And the problem for that is that we now have an answer that's a 3x1, but so that could be my first multiplication maybe here, if A was 5 and B was 6. But now I'm not able to multiply by the next one because I got a 4x4 times a 3x1. So if we forget this bottom row, then we would not get this extra 1 at the bottom of our answer. So we could not do the next multiplication. So if we need to stay ready to multiply other 4x4 matrices, we need a 4x1 answer. And so we need that extra row of 0, 0, 0, 1 across the bottom so that this one gets transferred over to there for the next multiplication. And then a kind of, I don't think that slide serves any purpose anymore. So I guess this is what it would look like in general if I didn't have, so I had specified a rotation matrix that was a pure Z rotation. We could do all of this in general, and this maybe gets to be a little weird, but the main thing is the X, Y, and Z are still just getting added to the result of our rotation matrix dot product thing, and the 1 is still appended to the bottom. So this 1, this column, and this extra row still add a displacement and pass the 1 along to the next answer, and neither this x, y, nor z ends up messing with the rotation of our PB vector times our RAB. So this is a general RAB that's any 9 values. We talked about how those 9 values are not all independent, whatever. So this is RAB times PB is here, but then added to that is the displacement of our origin and the extra 1 at the bottom. So someone else asks a question, does this always have to be 0, 0, 0, 1? And the answer is yes. Again, remember that the bottom row's only purpose is to take this 1 and transfer it over in the multiplication so that we're ready to do the next multiplication after that. If these were something other than zeros, then when we took this row and dotted it with this column, we would get U times PBX plus V times PBY plus W times PBZ plus a 1. And this is not what we want. Again, we want this result to just be a 1. The only way to ensure that that happens is to make sure that U, V, and W are all 0, so they blank this out and leave us with just that 1 that we want to pass on so we're ready to do the next transformation. So hopefully that makes sense and answers some of the questions that came up in terms of HT matrices and their use for TAB. And one of the things I wanted to push my students on was, okay, what if we now want to go the other direction so that we can just kind of understand HT matrices a little bit better. So if I want to find the inverse of an HT matrix, what I mean by that is a mapping of a vector known in frame A back to frame B. So I know PA. I need to rotate it into frame B components and then add that to a translation that's also expressed in frame B components. So it's probably safest again to think of that as a translation in frame B components and then adding to that this known position vector rotated into frame B. So if I think of that in that way, it's like I'm starting here, I'm translating like this, and then I'm rotating in the opposite direction of the other mapping. So not only is my translation going in the opposite direction. My rotation is now also in the opposite direction. And not only is this translation going in the opposite direction, but I need it expressed in frame B components instead of frame A components. So it'll turn out, I would call this vector P A org B, but it is not, again, not just the negative of P B org A, but it's rotated into frame B components. So when we get ready to try to find this TBA, we need a rotation matrix that's from B to A instead of from A to B, and we need this origin vector to point from the origin of B to the origin of A and be expressed in frame B. But we know from some of our previous discussions that the inverse of a rotation matrix is just the transpose, because it's an orthogonal matrix. And so what I want is RBA and PA org B. But I can find them in terms of the things that I already know by saying that RBA is really just RAB transpose, and PA org B is the negative of PB org A, but rotated into frame B components. But if I took this and substituted it in here, I would get this expression. So PA org B is just a negative RAB transpose times PB org A, where I would already have this and this from finding the TAB. Now I'm trying to find the inverse TBA. And so the final formulation of that is to say that I need RAB transpose up here in my 3x3, and then a negative RAB transpose times PB org A. But again, this, I think I say this in the next slide. So this is equation 245 in Craig's robotics book. The inverse of an HT matrix, or TBA, is RAB transpose and then a negative RAB transpose dotted with PB org A. But this is just another way of saying RBA, and this is just another way of saying PB org A. But we're formulating it in this way because we're assuming that because we already knew TAB, we knew this and we knew RAB, so it would be easier, instead of trying to find these things, to express it in this way. So that is what I'm trying to say. Hopefully that makes sense and is helpful.